Hello everyone, here I wanted to discuss motion in 2 dimensions, and let's first recall the kinematic equations and of course the free fall version of those. And what we're basically going to be doing is discussing problems where we will not be taking a look at using these equations or these equations in one problem. We're going to use both of them in one problem. So the problems we've seen where we have only horizontal motion or only vertical motion, now we're going to see objects that have this 2-dimensional motion where you can actually monitor some things that are happening vertically with each object. So in this case, it's going down, down, and then horizontally as well. So what I'm basically describing is that when something is moving in 2 dimensions, you can break it down into the horizontal and vertical aspects of that particular object. So in that case, we're going to take a look at these 2 types of kinematic equations. So the vertical version, or I guess the horizontal version I should say first, we're going to subscript everything with x's except for t, because time, as it turns out, is independent of direction. That kind of makes sense. And of course, delta x would be the horizontal component for displacement, whereas delta y would be the vertical component of displacement. So these would be vy's, v naught y. Negative g in this case is taken to be ay, and that's just a specific version that we'll be seeing very often in this class for the problems we'll be seeing anyways. But there are cases where these should have y's as well. There are problems where we don't actually do that. We don't replace ay with negative g, but that's mostly what we'll be doing. In fact, mostly we'll be having ax equal to 0 as well, because a projectile motion, so-called projectile motion problem, is where something is moving in kind of free fall, so to speak, in vertical, but horizontally there is no horizontal acceleration besides the initial push, so to speak. So there is still an initial velocity, but after that there's no thrust on the ball or anything like that. So for that reason, horizontally there's no additional acceleration. Okay, the reason why it is shaped like this, of course, it's kind of reminds you of a parabola, and that's what projectile motion really is. It's this parabolic shape of motion in 2 dimensions, and the reason why it has a parabolic shape is essentially because of this equation here makes it a quadratic in t, for vertical anyways. For horizontal, it gets kind of funny because if you plug in ax to be 0 for these equations, especially for the third one, the quadratic part actually goes away. But what that really tells us is that we can actually monitor the particular point of this. So let's say these are treated as points, and let's say this one in particular has a delta x displacement and a delta y displacement. If you solve for delta x, you can solve for it in terms of t, and if you solve for delta y, you can solve for it in terms of t squared. So basically what this will be is a point whose x value is in terms of t and whose y value is in terms of t squared. Basically, it tells you that the point is a quadratic over time. So it's going to have this kind of downward parabolic shape. And of course, the reason why it's downward is because the leading coefficient of t squared is negative because of gravity's downward, gravity's downward acceleration, basically. Good. So now, velocity is a vector quantity. In fact, I kind of been saying that all of these are vector quantities in the sense that here we're dealing with the horizontal components and the vertical components over here. So yes, velocity is a vector quantity, but so is displacement, like delta x and delta y are those components for displacement. Ax and then ay here being written as negative g are the horizontal and vertical components for acceleration respectively. But specifically for velocity, this will kind of come in play a lot. Given an angle at which an object is thrown, you can find the components of that velocity for that object. Now, this I'm writing this with a v, so you can kind of think this to be the final velocity. But of course, if you just subscript it with zeros or knots like this, then that actually also holds for initial velocities as well. So we'll be seeing all of this kind of come together in the following problem. So let's take a look at that right now and see how crazy it gets, I guess. Right, so here we have a pretty simple setup. In fact, this is a pretty classic kind of problem for a motion in 2 dimensions. So if a guy is standing on top of a building and he's throwing a ball at a certain angle, kind of like the picture I drew previously, only now we're elevated, and we're asked to find a few things. So we're only given three things really. We're given the height of the building, we're given the angle at which he throws it, and the initial velocity of the throw at that angle. So keep that in mind. So we're asked to find the time that it'll take for the ball to hit the ground. We're asked to find the velocity at impact, and we're asked to find the horizontal distance at impact. So how far away it'll land from the building. So of course you can kind of see that if you were to extend this arrow, something like this is what you should kind of imagine happening. So this is where we're going to land. Now we're being asked a few things about this particular point. How long will it take to get from where it started to where it ends? The velocity at the very, very end, and then finally the horizontal distance away. So let's see, how would we even begin this problem? Well, recall from the kinematic equations, there are the horizontal and the vertical components. So that's actually what I'm going to start off with. So allow me to kind of draw in this space here. So I'm going to erase this a little bit. So we start off with V naught equals 20, and we're given this angle. So right away we can find V naught x and we can find V naught y. So V naught x is going to be 20 times cosine of the angle, so cosine of 30, and then V naught y is going to be 20 times sine of the angle. So we'll find out what each of these are. Now of course, sine of 30 is 1/2, so this is going to be 10 for this one, and sine of, not sine, but cosine of 30 is radical 3 over 2, so this is going to be probably like 8.6, I think, 8.66. That's just kind of off the top of my head, and of course these are each in meters per second, but we can of course use our calculator to find out exactly what these are. And in fact, you know what, now that I think about this more, no, this is entirely wrong. This is 17.3, I was doing something different. Well anyways, let's just use our calculator to verify that. So I'm going to do that real quick here. So cosine of 30, yeah, 17.32. I'll just say 17.3. So we have our initial velocities for x and y. And in fact, you know, something I really, really want us to get used to is just doing the following. So I'm kind of erasing our pretty picture here, but that's okay. So we have horizontal and we have vertical. So what I'm going to do is I'm going to gather all of the bits of information we have, and remember that there are 5 different variables. So what am I talking about? Well, there's initial velocity, there's final velocity, there is displacement, there is time, and there's acceleration. Let me write time last. Okay, good. And there's a few things that we're going to learn from this. So this is V naught x and Vx. So for vertical, this is V naught y, Vy, this is delta y, this is Ay, and then there's time. Now the first thing you'll notice is, well hopefully, is that time doesn't actually care what dimension we're in. No matter if we're talking about horizontal or vertical dimensions, time is universal. It's dependent of the like length dimensions. So time kind of sits in between. So that's, I think, the best way of thinking of it. The time can kind of play a role of being in between these. It's independent of horizontal and vertical, is a better way of thinking of it. Now the reason why I do this is because very often we use time as a middleman to jump from one to the other. But in this question, we're asked to find time first, then to find these other things. So let's fill in everything we have, and then let's take a look. So we know V naught y, or V naught x, I guess I should say first. V naught x is 17.3 meters per second. Good. Also notice here the units are nice, everything's in SI, so that's good. We don't know the final velocity for horizontal, that's okay. We don't know delta x, we're asked to find that later on, that's okay. And we don't know AX, we kind of do, but we'll talk about that in a bit. V naught y, we know that's going to be 10 meters per second. Do we know Vy? We don't know Vy. Do we know delta y? We know delta y, kind of. So delta y is what? Delta y is it 45? It is kind of 45. So we have to think a little bit about what's going on. It's either 45 or negative 45, because remember that displacement can be negative and we're going down. So it's something to keep in mind. But here's the way I want to think of this as. So our initial y value is 40 meters above. And then our final y value is going to be, well, it's going to be here. It's going to be 0 meters above ground because we're going to be at ground level. So remember that it's final minus initial for delta y. So 0 minus 45 is indeed negative 45 meters. So if you ever get confused as far as is delta y negative or positive, just do final minus initial. Whichever one you want to be your final and initial. This I think makes more sense because again, we start 45 above and we end 0 above. So end distance minus initial distance. Now AY we also know that's gravity, and we're taking that to be negative because it's going down. So this is negative 9.81 meters per second squared. Or you can call it just positive, and then just keep in mind that when you plug this into the kinematic equations, that we're replacing A with negative G. So I know that sounds confusing, but there's two ways of thinking of it. Either we replace all AY's in the equation with negative G, or we can just let AY be negative this. But I'm just going to do it like this for right now, so you'll see what I mean. Good. So now can we find T? And I think we have enough information here to find T from the vertical side of things. Not quite from the horizontal side of things, but we'll talk about that shortly. So now all I need to do is figure out which kinematic equation should we use. So obviously it's best if you have a list in front of you, but I believe the one we want to use isn't the first one, nor the second one. It is definitely going to be the third one. So the third kinematic equation tells us that delta y is equal to v naught yt minus g, I guess it's 1/2 g, so minus 1/2 g t squared. Now notice since g is 9.81, we get this. And we also know what v naught y is. So you know what, let me do this. Just so it's a little easier for me to understand what's going on here. So negative gt squared, and like I said, g is positive 9.81, not negative, because then you get a double negative. So the way I'm using this equation here, and I know again it sounds a little confusing, is that I'm replacing all ay's with negative g's, but if you wanted to use this negative, you can think of this as positive 1/2 ay, and now ay is replaced with negative 9.81. So I think that sounds a little better. So delta y is equal to v naught y, that's 10 times t, minus half of 9.81 is 4.905 t squared. And we know what delta y is actually. Delta y is negative 45. Perfect. So now can we find t this way? We certainly can. Just trying to think for a moment if that's exactly what we want to do. There's probably a better way of doing this, but let's do that right now. I think it's worth it because we had to see this sooner or later. So what I'm going to do here is I'm going to rearrange this in a specific order. I'm going to move everything on one side so the zeros on the other to get this in, of course, like a standard quadratic form. So you can kind of think about what I'm doing here, but I'm just grabbing these two terms on that side, subtracting and adding them to this side so that we have our quadratic form. And then we have a 4.905, b is negative 10, and c is negative 45. And if you haven't figured it out already, yes, I'm using quadratic formula. So that means t is going to be negative b, so positive 10, plus or minus the square root of b squared, that's going to be, let's see, b squared is going to be negative 10 squared is 100, minus 4ac, so 4 times this times that, that's going to be positive though. So now, let's see, so 4.905 times 45 and then times 4. So I get 882.9, and then plus 100, that's going to be 982.9. And all divided by 2 times a, but since a is half of gravity, 2a is just going to be gravity itself. So again, I know I'm not really showing too much work here as far as what the quadratic formula actually is, but that's something that you should have seen before in algebra. And if you're curious, I'll just write it here off to the side in t. So I'm using negative b plus or minus the square root of b squared minus 4ac, all divided by 2a, where at squared plus bt plus c is equal to 0. So that's our quadratic formula. Perfect. Okay, so now let's figure out what this is. So I'm going to use my calculator to compute this right now. All right, so using my calculator, I use actually the positive root here. As it turns out, radical 982 is about 31. So 10 minus 31 would give you negative 21, which will give you negative time, and time can't be negative, of course. So we're going to go with a positive one, and that gives us a time of 4.22 seconds. So it takes about 4.22 seconds to hit the ground, and there we go. So we finished A. And we can now write in our chart here, t is equal to 4.22, and I'll write SEC for seconds. Great. But now there's still a few other things that we haven't really found out. And if you want to complete, we can actually find Vy. How can we find Vy? Well, there's a few ways to find Vy. Now that we know what t is, we can use any equation we want, honestly, that involves Vy. And in fact, the one I'm going to use is the first kinematic equation. So let me just erase that here real quick. So the first kinematic equation is Vy is equal to V naught y minus gt, or I guess it'd be plus ayt. And since ay is negative 9.81, and we don't know Vy, but we know V naught y. V naught y is 10. And then this is going to be plus negative 9.81 times time, which we now know to be 4.22. So now using my calculator here, we can calculate what the final velocity is. Notice it looks like it's going to be negative, so let's see what that's all about right now. Right, so this is what I got with my calculator. I got negative 31.4 meters. So I'll write that here, 31.4 meters per second, I meant to say, because it's a velocity, of course. But now, why is it negative? Well, it should make actually a lot of sense why it's negative, because if you recall, velocity is displacement over time. Since our displacement is negative, it's going to be a negative velocity. So throwing the ball up would be a positive displacement, hence a positive velocity. But then when the ball comes back down, it's a negative displacement, hence a negative velocity. So the final velocity being negative actually makes a lot of sense. So by the way, this final velocity is at the end of these 45 meters because we use those 45 meters to compute that time. And after that time, then it'll land 45 meters below its initial throw. So this is actually kind of like the velocity at impact, but notice velocity at impact is a little particular because here we found the vertical velocity at impact. The horizontal velocity at impact we're going to find right now. And in fact, notice I kind of skipped mentioning what AX is. What I mentioned earlier, AX is usually 0. Yeah. I don't know if anyone actually said it with me, but that's okay. And it's usually 0 because, well, there's no additional acceleration unless you consider wind or something crazy, or if the ball had thrusters on it, for instance. But after the initial throw, it's just on its own, basically. So horizontally, there's no assistance, or if there's no wind, then there's no, I guess, resistance. But of course, gravity in this case will be assistance, and in this case will be resistance. So throwing it up, it'll come back down, but then throwing it down, it's going to go faster and faster. So I hope that makes a lot of sense. So with that being said, since AX is 0, a lot of those equations for the horizontal side of things actually become a little shorter. In fact, one we'll be seeing that involves delta x is, let me kind of write it over here. In fact, really it's just this, only with x's instead of y's. So I'm going to change this, replace all of my y's with x's, and notice since ax is 0, that makes that second term on the right-hand side go to 0. And we're just left with delta x is v naught x times t. And we actually know what v naught x is. That's 17.3. And we also know what t is. T is 4.22. So now let's crank this out using our calculator. And I actually got about 73 meters. So honestly, this is probably the best way of handling any two-dimension projectile motion type of problem. Create this chart with all of the variables in sight. Just fill out the chart and then answer the questions afterwards. But we're kind of answering them as we go along. So notice we kind of skipped B for a moment's time, and we actually know the horizontal distance at impact, it's just going to be 73 meters. So I'm not actually answering it in the order that they would like us to answer it, but that's okay. 73 meters away from the building. Good, so now finally we want the final velocity. Now I just jumped to this, but honestly we could have found final velocity using the exact one we used here. So notice, and this is kind of funny, but notice we had V naught, or not V naught, but Vx equals V naught x, there we go, plus AXT. But since AX is 0, then that means Vx is equal to V naught. Vx equal to V naught x. And that makes sense because since we have 0 acceleration, that means we're not speeding up nor slowing down horizontally. So horizontally, our final velocity is equal to our initial velocity. Now again, this whole velocity and impact, that's a little vague. So what that I think is trying to say is, what is the speed at impact? Now remember, speed is the magnitude of velocity. These V naught x and V naught y's are the magnitude of the components of velocity. So really what I want to do is I wanted to take a look at V naught x and V naught y, and I'm going to try to draw a picture here. I'm going to erase a few things. So unfortunately I have this over the picture, but I'm just going to redraw the impacting part over here. So let's just imagine this is the floor and this is our point of impact, and the ball is following this trajectory here, and it's at this specific angle. So if we want to find the angle of impact, we can do that. Remember, tangent inverse of the opposite over adjacent sides, that's Vy over Vx. If you want to do Vy over Vx, take tangent inverse of that, that'll give you the angle. We could do that. I'm not going to, but you can. Similarly, the magnitude of the vector at the point of impact we can find out as well. And that, well again, so it's going to be negative here. But look, so I think it's a little hard to describe just because of the image looks a little weird. But the velocity is like this, so it has a vertical component Vy and it has a horizontal component Vx, like that. So remember that how you find the magnitude is by taking the square root of the sum of the squares of the magnitudes of the components. So namely, we're going to square Vy and Vx, add those together, square root that result. So I'm going to get 17.3 squared plus negative 31.4 squared. Add those results together, square root that, and let's see what we get. So after using this in my calculator, I got about 35.9 meters per second. I was going to say squared, but that would be acceleration. So 35.9 meters per second. Which is kind of crazy because it's more than either of these, but that's usually what happens, because if you have a vertical velocity of about 30 and a horizontal velocity of about 17, then your actual velocity in that particular angle will be more than that. Kind of think of a right triangle, the hypotenuse is always larger than the other sides. Okay, good. So this is about 35.9 meters per second. Perfect. So all problems involving motion in 2 dimensions, to be quite honest, are basically just like this. We're going to be taking a look at another one that's a little different, but you'll see it's very, very similar. The setup's similar, the way we're going to be solving is similar, but I'm just going to try to do a little faster given that we saw how we did this as far as the technique goes. So let's take a look at that problem right now. Right, so like I was saying, I'm going to try to do this problem a little faster than the previous one because we've kind of learned a lot from the previous example. So it looks pretty similar. Let me try to explain what's going on. We have a guy kicking a ball outside of a playground that he found 24 meters away from the building. The playground is actually located on top of the building, 6 meters above, but there's a 7-meter barrier protecting the children from falling off the building, basically. And he's kicking it again at 53 degrees. And the time it takes to get to the wall itself is 2.2 seconds. Now notice it's not going to touch the wall, it's going to be above the wall. But to get to that vertical line, it takes 2.2 seconds. So notice here I've also filled out kind of a table for us that we're going to fill out all of these variables, just like we did the previous problem. Okay, good. Now we're asked to find a few things. We want to find the initial speed. By the way, in the previous problem, we found the final velocity. I actually gave you the final speed. Remember, the velocity is a vector quantity, meaning that technically you need to find the angle. I told you how to find the angle, but I didn't quite do it. So technically you would need that to find the velocity. But to find the speed, that's just the magnitude only, which we found in the previous one. So here we want to find the magnitude only, which we'll talk about. And then notice we would kind of need each component. So we need to find v naught x, v naught y, and then we can maybe group those together somehow to find v naught. So we'll do that in time. B asks us to find the vertical distance of clearance. So that's kind of like the distance here, total distance from the ground minus 7. And I kind of made that like with this little red distance here. I don't know if you can quite see it or not. Now I made it maybe a little smaller than it needs to be. It may actually be a lot taller above or a lot higher above the wall, but we'll find out. And then from there, the horizontal distance from the wall that it lands on the opposite side of where the guy is. So let's see if we can figure things out here. So first off, do we know, what do we know? Well, remember, it takes 2.2 seconds to land to this point. So that means at this point, we have delta x. Delta x is 24. So 24 meters is delta x, so we'll fill that in. Also notice I've included for us the horizontal acceleration being 0, because again, it's a projectile motion problem where there's no additional assistance nor resistance on the ball. And gravity is, of course, is negative 9.81 because it's going down. Gravity is going down. Good. So we don't know delta y, we'll find delta y. That's actually what we want to find here. And what else? V naught x and v naught y. Well, we're asked first to find the initial speed. So maybe actually we have enough to find v naught x and v naught y. So let me just say this. Yeah, I think I'm okay to say the following. So notice that we had this equation, delta x is equal to 1/2 plus v naught x plus vx times t. Now, since the acceleration is 0, then that means there's no change in velocity horizontally. So these are the same. So I can call v naught x equal to v naught, or v naught x equal to vx. And then when you add them and divide by 2, this equation really just collapses to this one. Since we know time and we know delta x, we can find v naught x. So v naught x is just delta x divided by t, which of course is 24 divided by 2.2. So let me calculate that real quick. So my calculator gave me about 10.9. That's going to be, of course, in meters per second. Now the huge issue is, can we use this to find v naught y? And maybe we can't use it directly to find v naught y, but we actually can use it because something we haven't considered yet was the angle, which is kind of strange because we haven't really seen too much of that going on. Usually we use the angle to find v naught x and v naught y, but here we found v naught x using something else, and now we're going to use the angle to relate them. So let me erase this real quick, and what I'm going to write is something a little different. So here what we know from vectors is that v naught is equal to v naught x, kind of said it backwards, v naught x, there we go, is equal to v naught times cosine of the angle. Now we know the angle is 53 degrees, we also know v naught x, we just found that, that's 10.9. So we can actually just divide both sides by cosine of 53 to find v naught. So let's plug this into our calculator right now and see what it gives us for v naught. All right, so I got about 18.1, and that of course is going to be in meters per second because it's a velocity. Now this is the initial speed. This is the magnitude of the initial velocity, so that is actually our answer for A. But of course we can use this answer to fill in the rest of the table as far as the initial velocity for the y components go. Because we know that v naught y is equal to v naught times sine of the angle, which is 53 degrees. And since we know that v naught is 18.1, then all we really need to do is multiply 18.1 to sine of 53, and now let's use our calculator here to see what we get. And if you round up, you get about 14.5, and again, that's in meters per second. So let me fill in our table here, 14.5 meters per second. Very good. And now we can move on to part B. I don't think it's going to be too bad, actually. We want to find the vertical distance of clearance. Basically, we want to find delta y. So let me erase some things here, and let's see if we can kind of figure out which kinematic equation we need to use in order to find delta y. So we have, for vertical, because we want to use a vertical kinematic equation, of course, we need to use an equation that involves v naught y, delta y, because that's what we're trying to find, gravity, so ay, and then finally t. And the one that I think of that kind of keeps coming up quite a bit is delta y is equal to v naught y t plus 1/2 ay t squared. Good. So let's plug some things in and see if we can solve for it. In fact, it's already isolated, so it's going to be basically just a plug and chug. So we get 14.5 times 2.2 plus, we know 1/2 of gravity is it's going to be negative 4.905, and then times 2.2 squared. So let me use our calculator here to see what we get. Okay, so I got about 7.9 meters. And what does that tell us? Well, we know the wall is 7 meters tall, so that means the difference here is going to be about 0.9 to complete the 7.9 meters. So 0.9 meters, which is about, I think, 90 centimeters, because again, there's 100 centimeters in every meter. So this is 0.9 meters, so that's going to be 0.9 times 100 centimeters, which is 90 centimeters. So that's kind of nice that we can see that in a little bit of a different unit. It's more manageable for us. But still, that's okay. And of course, if you want to convert it to feet, you can do that as well, but I'm not going to go that far. Now, C asks us to find the horizontal distance from the wall after landing on the other side of the wall. This is going to pose a little bit of a problem because our time is now out the window, because we don't care about this vertical barrier. This is also out the window, and this is also out the window. So we kind of have to restart for problem C. So let's see if we can erase some of the things here that we have now no longer as a part of the problem to see if we can figure out how to crack C. Right, so I've cleared some things up, and of course maybe I got a little too carried away when I crossed out 24. We kind of need 24 because we want the distance from the wall on the other side, so we're going to do some subtraction at the end. Now we know delta y from here is going to be 6 meters. And again, we know it's positive, of course, because that's our final height. Final minus initial would be 6 minus 0, which is 6, so that's good. We don't know time, but maybe we can find time. After all, we want to find delta x, and in this scenario, by the way, delta x would be this distance, horizontal distance from the point of landing, to the point of landing from the point of launch. So this is delta x. So we actually want to find this distance, which is the difference between delta x and 24. So we'll find that after, but for right now, delta x is this distance here. That's what we want to find. Now we don't have a lot going on with horizontal, but we do have a lot going on with vertical. So we're going to, of course, use vertical to find time, and then finally use time to find the horizontal delta x. So let's see if we can find time here. And yeah, the only, again, it's going to be just like the previous problem. We have to use quadratic formula. So I'm going to use delta y equals v naught yt plus 1/2 ay t squared. So plugging things in, we get 6 is equal to, that's going to be 14.5 t. Hang on. You know, I think I'm realizing now that this initial velocity may be different because actually the initial velocities are the same still. I'm glad I'm bringing it up though. The reason why the initial velocities are the same still is because it's the same problem overall. Even though we took away that time 2.2, it still takes 2.2 seconds to get to this vertical line. So we would still have to have these initial velocities to make that timestamp happen. So these are still legit. Got kind of worried for a second there. So minus half of 9.81, that's 4.905. And then times t squared. And then if we move things around, so add and subtract these respectively to the other side, we get 4.905 t squared minus 14.5 t plus 6 is equal to 0. So using quadratic formula, much like we did in the previous problem, let's see what we get. We get negative b, so it's going to be positive 14.5, plus or minus, remember we took the plus one, but let's see what happens here, times the square root of b squared, which we'll have to calculate what that is, minus 4 times a times c, all divided by 2 times this, which is just gravity, 9.81. So I'm actually going to use my calculator to figure out what the inside of the radical part is. So I'm going to do 14.5 squared minus this times this. Now notice they're both positive here, so that can be a little weird, but let's take a look at that right now. Right, so that was a little bit of a close call. We actually end up getting bigger minus smaller, so we don't have the issue of having the negative inside of the radical, which would be alarming, but that's good. So actually what we end up getting, if you take the sum of the two, there's kind of an important story behind this, but if you take the sum of the two, you get 2.59 about, it rounds up to 2.59 seconds. Now, if you actually do the plus or minus, for the minus scenario, you get about 0.37 seconds. So what exactly does this mean? Why do we get two different times here? What's exactly going on? Well, notice it takes 2.2 seconds to get to this wall. So 0.37 doesn't make sense because that's less time. In fact, if you take a look at what's really going on here, if you draw a horizontal line extending from the point at which we land, there's actually 2 points where the ball reaches 6 meters above the initial launch. One is right here at 0.37 seconds, and the other one is that 2.59 seconds we just got. So that is actually our answer there. So now again, we're going to use this with horizontal things we already have to find delta x. Then we'll subtract that, we'll do that minus 24, and then we'll get this. So let me clean this up and let's handle that right now. Okay, perfect. So now which kinematic equation are we going to be using here to find delta x? And it's of course the one we've been using. It's delta x is equal to v naught xt. Because of course, this isn't really a kinematic equation, but that's kind of what you get when you consider ax to be 0, because there's two ways of doing it. But again, if you write delta x equals v naught x times t plus 1/2 axt squared, that goes to 0 because ax is 0. Similarly, if you use the fact that this implies that v naught x and vx are the same, they're both 10.9 meters per second, then you can use the second kinematic equation, not v naught x, but delta x is equal to 1/2 v naught x plus vx all times time. So then those two combine to just be one of them, and then half of that, or 2 times one of them, and then half of that will just give you one of them. So we end up getting this either of those two ways. And v naught x, of course, is 10.9, and time, of course, was 2.59. Multiplying these gives us, let's see, I got about 28.2, and that's again meters. Perfect. So we have this table completely filled out for our purposes. And now what? Well, now we want to find out the horizontal distance from the wall, and that's the difference between this and 24, and that's of course going to give us 4.2 meters. So 4.2 meters on the other side of the wall is where it will land. Perfect. So yeah, it was kind of a long problem. These two-dimensional problems, two-dimensional motion problems generally will take that amount of time. They're all pretty similar though. So that's all I really wanted to do for this lecture on motion in 2 dimensions. And then next I believe we'll be talking about forces, which also kind of gets a little involved as well, but we'll kind of see that all of this will kind of connect in a really magical way. So I'll see you in the next video for that. Thanks for watching. See you then.